All right, so welcome back to Chem 140A. What we're going to do now is sort of move on from sort of the fundamental physics side of solid state physics and get into what real systems look like. So we sort of discussed the physics behind periodic systems. And we did some pretty simple periodic systems. We did sort of like one-dimensional arrays of atoms. But there are real life examples of periodic systems. We call them crystals. And they have tons and tons of different structures. And the math behind them is obviously a little bit more complicated, but the results are basically the same as what we found in one dimension. So if you can sort of understand how you get to band structure in one dimension, you can understand why band structure might appear in 3 dimensions. There's a lot of different structures. You've probably encountered a few of them before, but the most relevant crystal structure for semiconductor physics is called the face-centered cubic structure, or FCC. And it looks like this. So it's a cubic because we have like one atom at each corner, and it is face-centered because there is another atom at the center of each face. Now, this structure that I've drawn here is called a unit cell. And we encountered that before. I sort of used that terminology when we were doing the fundamental physics with the chronic penny model. And so what a unit cell is it's like the most fundamental repeating system in our crystal. So this is the smallest structure that I could draw that is then repeated over and over again in our semiconductor system. So this is going to be sort of a model that we use a lot when talking about different crystals, because remember when we were doing some of these models, we really only cared about doing the math in those small unit cell areas. Well, similarly, if you can understand the physics going on in the unit cell, you can often extrapolate that to what happens in the bulk. So the most basic semiconductor structure involves 2 FCC lattices mixed together. So you kind of put one inside of another. It's a little bit difficult to visualize. There's some tools online that you can look at if you wanted to see. But what it does is it produces a diamond tetrahedral lattice. So this is what you find in some of our intrinsic semiconductors like silicon and germanium. So I'm going to try to show you how this is like the same system. So there are 2 different colored atoms in here. So there's the black ones and the white ones. And the black ones are part of one FCC lattice, and the white ones are part of a different FCC lattice. So for silicon and germanium, they're all, either silicon or germanium atoms, but they're 2 different FCCs. So let me see if I can show you. So let's imagine that atom right there is going to be this corner, right? So then if you go up here, that's going from here to there. And then if you go to this atom, that's going from here to here. And then from here to here is from here to there. Hopefully that helps you see it a little bit better, where like the corner of one of the FCCs is sort of inside the other one. It's a little tricky to visualize, so don't worry if it's too complicated. You just need to know that there are 2 FCC lattices in here. So this is your diamond tetrahedral lattice. Lots of semiconductors adopt this structure, especially what are called the adamantine semiconductors, which are the ones that have an average of 4 valence electrons. So that's silicon and germanium, which actually do have 4 valence, or some of the compound semiconductors like gallium arsenide, or let's say cadmium. Yeah, or actually I don't know if cadtel has the structure, but I think indium phosphide does. So like say indium phosphide. So silicon actually does have 4 valence electrons, but these are called 3s/5s because gallium has 3, arsenic has 5, which leads to an average of 4. So in that case, if you have a compound semiconductor like say gallium arsenide, which adopts this structure, remember how I said that these are 2 lattices put together? So one of the lattices is actually like just gallium, and then the other lattice is just arsenic. And so in that case, these 2 different colored atoms that you're seeing here are actually 2 different atoms in that case. And that's called zinc blend because technically it's not perfectly, symmetric and all that because like you have 2 atoms of 2 different sizes. But zinc blend and diamond tetrahedral are basically the same thing. Just zinc blend has 2 different atoms inside of it, whereas diamond tetrahedral is all the same. So then there's others which adopt, say, like the Wurtzite structure, which only has like half of its tetrahedral sites filled, which is like really hard to draw. But imagine, take this and I don't know, I think it's like maybe taking like that one and that one out, something like that. It's a little difficult to draw, but suffice it to say that like only half of its tetrahedral sites, which by the way are these sites. These are the tetrahedral sites. Because if you notice, look, there's 1, 2, 3, 4. It forms little tetrahedra inside there, which is why they're called tetrahedral sites. So half of those aren't filled in a Wurtzite. Then there's other structures like TiO2 is known for having some different structures like anatase and rutile. There's your layered materials like molybdenum disulfide, tungsten disulfide, tungsten diselenide. There's lots and lots and lots of different structures. And if you want to know more about like all the different structures and like, hey, this semiconductor that I might be working with, what structure does it have? You can look into some material science textbooks and they probably have that for you. But if you want more on that topic, take an intro to material science class. For us, we just need to know that these crystals exist and we want to know some of the basics. So now that we understand sort of what a crystal looks like, these different unit cells, we're going to need some basic concepts of material science. First one is crystal planes. So you're going to run into a lot of notation. So these are like Miller indices. And so what they do is they tell you either like what direction or what plane you're looking at in a crystal. So I have drawn some XYZ axes. We're going to assume it's sort of like a basic cubic sort of thing. We're not going to mess with hexagonal coordinates in here. That's a little complicated and not super relevant to most semiconductor systems. So a 1, 0, 0 plane is a plane which intersects one of your axes at some point 1 and then 0 and 0, saying that it never intersects with the Z or the Y axis. So you can equivalently draw a plane that's like in the Z axis here. So like here, right? Where it only intersects with the Z, never intersects with the X or the Y. That's the same thing. In that case, that would be 0, 0, 1, right? Because it would intersect only in the Z, not in X or the Y. But then together, we would call that family. So like a plane that only intersects with X, only intersects with Z, or only intersects with Y. We're going to call that the 1, 0, 0 family of planes. So that's what those different brackets mean. So we have our 1, 0, 0, which is, again, intersecting just 1. Then we have our 1, 1, 0. So just like before, we're going to intersect X at 1. And now we're going to intersect Y at 1. And we're never going to intersect Z. So it's going to make sort of this triangle shape. And again, you can do this with other axes as well. but that gives you sort of this triangle face sort of pushing outwards, or it'll give you the triangle here, excuse me. That is the triangle I'm referring to. And then it just sort of like goes out in this direction. Then the last one that we have to look at is the 1, 1, 1. So that intersects the Z at 1, the X at 1, and the Y at 1. So that makes this sort of triangle here. Now, just to be clear, you're not actually making a triangle. You know, these are planes, so all of these are completely infinite. But this is the way it's drawn a lot of the times, just because you want to restrict it to your graph. But remember, these are all infinite planes that are stretching out in all directions, but this is sort of the angle that you're looking at. So those are sort of the important faces to consider. The 1, 0, 0, which intersects only one of your planes, or only one of your axes, the 1, 1, 0, which intersects 2, and the 1, 1, 1, which intersects all 3. So one of the things that's important to understand with these is if you look at a crystal, right? Let's just draw, let's just draw a crystal, right? I'll keep it simple. We'll make it a cubic crystal. So it's cool to think of that as like a unit cell that's like buried somewhere deep in the bulk of our crystal, but crystals end, right? We're not working with theoretical crystals anymore. We're working with real ones. So somewhere this crystal here is gonna touch air or vacuum or whatever. So it's sometimes important to know which face is touching air, like what is the terminal face. That can affect its chemistry quite a bit. So for example, with this crystal here, you know, does it intersect, you know, right here on the top? And like what plane would that be, right? So in that case, you know, if we draw our axes here, so we have our Z, our X, and our Y. Notice that intersects with the Z, not with X or Y. So that is going to be the 0, 0, 1, or the 0, 0 family of planes. Now, cool. What if that's not the way the crystal grows? What if it grows in a different way? So what if that crystal, maybe, you know, we have this cube here. I know it's a bad cube, but, you know, work with me, right? What if the crystal gets cut off here? What if it terminates in a 1, 1, 1 face? So now what's actually, instead of having a square repeating unit that's contacting your air or vacuum or whatever your interface, now we have sort of this triangular thing, which is going to repeat over and over again. So that's going to look different. That's going to be a different surface that's facing out. And the reason that we care about that is, I mean, you're in a chemistry class, right? And chemistry occurs at surfaces. So if we are looking at different faces that are composing the surface, we're going to get different chemistries. So that's why that's really, really important. And in fact, one of the more important things to understand is how many atoms there are per face, because that can change the number of atoms that's actually at your surface, which is kind of like changing the concentration of like some molecule in solution, right? So if you're looking at one face and it has, I don't know, like 1,000 atoms per square centimeter, which is tiny, but let's just say 1,000 atoms per whatever. And then you have another face which has, say, 2,000 atoms per whatever. That second face, which has twice as many atoms on it, can do twice as many reactions, right? At least theoretically, assuming we can access them all, right? But that's like doubling your concentration. So your faces are going to look different. So like if you reacted something that's going to, let's imagine it's like gold, right? And we're putting a thiol molecule on there, which forms like these self-assembled monolayers. You get like gold here, and you get like an S and then some garbage, S and then something here. So this would be one face of the gold, but what if there's a different face which has like an extra atom here? So now we can have more of these at the surface. Okay, so I think that's enough justification of why we care about crystal surfaces. Let's actually calculate how many atoms there are per face. I'm going to use FCC just because it makes my life easier, but you can do this with any crystal face, including the diamond tetrahedral. So let's look at the 1, 0, 0. In this case, it's actually a 0, 1, 0, but that's fine. So if you look at that, so that's going to be this face of the crystal here. So let's pull that out, and we're actually going to draw like circles for our atoms, and then we're going to draw the face, and we're going to put the vertices right in the center of those atoms. Because what you find here is not what you might like jump to. You might say like, oh, let's look at this, this FCC right here. And there's 1, 2, 3, 4, 5 atoms there. So there's definitely 5 atoms per face. Well, no, not quite, because remember, this is a unit cell. This is a periodic system. So there's actually another face here and another one here and here and here. Right? So it's, these are shared in between all of these. So we need to take that into account. So what I've done here is I've shaded them in green in the fraction that's actually shared by each face. So in this case, we have 1/4 of each of the corner atoms and the full thing of the center. Right, that center atom is going to be completely unique to that unit cell. So we have 4 of the quarter atoms and then 1 of the center atoms, which gives us 2 atoms per face. Right, so it's a little non-intuitive. What about for the 1, 1, 0? So in that case, we're going sort of diagonal, and we're going to catch these corner atoms. And for an FCC, oh, I actually missed. There should be 1 there and 1 there. That's a mistake on my part. There should be shading in there. All right, but we're not catching anything in the middle. There's nothing there. But there are atoms here and down here, which I missed the first time. So in that case, we have 4 times the quarter atoms. And now we're also going to add plus 2 times 1/2. So that is going to be equal to 2 atoms per face again. Right? That makes sense. Yeah, I'll get rid of that. Okay. But also notice that the surface is different, right? This FCC does not look like the 100 does not look like the 110, even though they have the same number of atoms per face. Now let's look at the 111. So again, we're going to sort of intercept a couple of different atoms here. So we're going to now have these little weird corner things, and then you could actually do the math to figure this out, or just trust me that it's 1/6, because these are going to be equilateral triangles, right? So we're going to get 1/6 of these atoms here, and there's 3 of them. There's the 1, 2, and 3. And then we're going to have 3 of the half atoms, these guys here, which are going to be from your face right there. And that's, again, going to give you 2 atoms per face. So for our simple FCC, we're going to expose the same number of atoms per face on average, but that's not necessarily true for all. That's not necessarily true for all different systems. And that's how you look at counting them. So if you, I think on your problem set, you have to calculate the number of atoms per face for a diamond tetrahedral. So just make sure you're counting your fractions correctly. And double check me on this. I did this a little bit quickly, but I will be there to help you with the 3D or with the diamond tetrahedral. Okay, so we calculated the number of atoms per face, which is kind of where you're exposed, right? But it can also be important to know how many atoms you have per cubic centimeter, right? So how many atoms do you have per unit cell volume? This will be really, really important when we start looking at things like carrier concentration. So like how many electrons are there per number of atoms? And that'll be really, really important when we get into dopants and looking at, okay, how many dopant atoms do we actually need to make a big change to how our crystal behaves? So we want to know not only the number of atoms per face, which can tell us about the chemistry, but also the atoms per unit volume, which can tell us about sort of the fundamental properties and how we can alter the properties of a bulk crystal. So let's calculate this. So I'm going to use, just for a ballpark estimate of how many you should expect, the FCC lattice, again, because it's easy, with silicon lattice constants. So I'm just going to use the silicon lattice constant, which is A is equal to 5.4 angstroms. So each side here, the lattice constant is like the length of each side here. The length of each side of this cube is going to be 5.4 angstroms, which an angstrom is 1/10 of a nanometer. Okay, so let's look at our unit cell. We have one atom at each corner, which remember before on our faces, each one of those we got like 1/4 of it, right? But now we're in 3D and we're not getting 1/4 of it anymore. We're actually getting 1/8 of it. Because if you imagine looking at your sphere, right? So we have sort of this kind of number, and we are only getting sort of this chunk here. That's the only part that we're actually getting. So that would be, remember, so you got like 1, 2, 3, and 4, because remember, you're kind of dividing your circle like this on the top as well. And then you have that again on the bottom. So you have 4 segments on top, 4 segments on the bottom. That's 8, and we only get 1 of them. So for each corner, you get, so each corner atom, and there are 8 of them, you get 1/8 of an atom. Then for each face, which we have 6 of, let's look at how many atoms we get. So in this case, that there, so half of it is sort of sticking into our unit cell, the other half is sticking out, and that's the half we don't get. So we get about half of it sticking in. So once again, for our face atoms, we get half of it. So we get 8 times 8, 6 times 1/2. So we get 3 and 1 for a total of 4 atoms per unit cell. Okay. So we know how many atoms per unit cell we have. We know what the size of the unit cell is. We're going to cube that to get the volume. So 157.46 angstroms cubed. So now we have 4 atoms per unit cell. And then we're going to divide that by the number or by the volume, which is going to be 157.46 angstroms cubed per unit cell. Which, remember, we're going to do some dimensional analysis. So it's like atoms per cell divided by angstroms per cell, which is going to be like multiplying by cell per angstroms cubed. So that's going to cancel out. So we're going to get atoms per volume, right? And then we're just going to convert the volume. So we're going to do that. And then here's just our conversion factor over here. 1 angstrom, remember, is 1/10 of, 1 angstrom is going to be 1/10 of a nanometer. So it's 10 to the minus 10 meters or 10 to the minus 8 centimeters. And then we're going to cube that. There we go. All right. So expanding on our equation here. So we get 4 over 157.46 multiplied by this thing, because 10 to the minus 8, 10 to the minus 24. Then you get this, so 4 over 1.57 times 10 to the minus 22, which ends up being about 2.5 times 10 to the 22nd atoms per centimeters cubed. And this factor here, that 10 to the 22, keep that in mind. Because you're going to find that fairly frequently. Oh gosh, that's this again. There we go. You're going to find that fairly frequently in semiconductors. It's typically going to be, so the number of atoms per cubic centimeter that you get is going to be typically on the order of 10 to the 22. So that's also interesting because remember Avogadro's number is 6.022 times 10 to the 23rd. So 1 cubic centimeter of semiconductor is approximately equal to a tenth of a mole. And then when you calculate the number of atoms per face, you can then consider like how many atoms are there actually there per cubic centimeter? Probably less, right? And so that'll have some impacts on its reactivity. Okay, so that sort of wraps up this semiconductors lecture. So in summary, we looked at different crystal structures, especially those that are relevant for semiconductors like FCC and diamond tetrahedral and zinc blende. And then we used those and calculated the number of atoms per face and the number of atoms per cubic centimeter, which will give us sort of a framework, sort of an idea of how to think about the chemical reactivity of these surfaces going forward.